Welcome students. We want to talk about separable differential equations now. So in last class, we learned about method of integrating factors. Note that the method of integrating factors for solving a differential equation only work for first order and linear differential equations. Okay. So now in this section, we want to basically move from linear to nonlinear, but still keep the first order. So we want to solve for nonlinear first order differential equations, and not to all of them, but a special class of them, which is called separable differential equation. Okay, so what is a separable differential equation? So separable equation, first order separable equation, has a form dy by dx, which is equal to f of xy. So this is the first order differential equation. Now any first order differential equation can be changed, can be modified to look like m of xy plus n of xy dy by dx equals to 0, all right, for some function m and n. So this is how any first order differential equation looks like. Now, what makes it separable is the following. It is that you can write your m of xy as a function of x only, and you can write n as a function of y only. So in some sense, you're trying to separate all the x on one side and y on the other side. So this is the idea behind the separable differential equation. So what is a separable differential equation? A separable differential equation is a first order differential equation, mxy plus nxy dy by dx equals to 0, if your m is just a function of x and n is just a function of y. So let's look at an example. An example would be v plus x dv by dx equals to v minus 4 divided by 1 minus v. Okay, so question, is it separable? So then the question is, can we separate all the v's on one side and x on the other side? So let's try to work on that and see if it's separable. So question, is this separable? Is this separable differential equation? So you can see that if I bring this v on the other side, I get dv by dx equals to v minus 4 upon 1 minus v minus v, right? So now I can write this as dv upon v minus 4 upon 1 minus v equals to dx. So you see I've separated all v on one side and x on the other side. So no, sorry, this x should have come down here. So this is an example. Yes, this is a separable differential equation. All right. So one. Another example could be, we have x dy by dx equals to square root of 1 minus y square. The question, is this separable? So let's try to see if we can separate y and x on the other side. So we get x. So we can write it as, say, dy over square root of 1 minus y square equals to dx over x. So yes, it is separable. Separable. Okay. Let's give an example of non-separable. For example, t minus 3 y prime plus ln t of y equals to 2t. Is this separable? No, you can't really. You can see that you can, if you, even if you try to separate it, you will not be able to separate. So non-separable. Yeah. However, we know how to solve this using what? Using the method of integrating factors, but that's another story. So then the question is, how can we solve any separable differential equation? So let's see an example. Let's see how does it works, its method. So, so separable differential equation. So separable differential equation looks like mx plus ny dy by dx equals to 0. Yeah. So let y equals to phi of x be the solution. The solution to differential equation. So if y equals to phi x is a solution, then this equation can be turned into m of x plus n of, instead of y, I will write phi of x. Instead of dy by dx, I'll write phi prime of x. And that is equal to 0. Right? Now this implies what? I can take m dx, mx dx, if you want. Let's write that to indicate that it's a function of x, plus integration of what? N of what? Phi of x times phi prime of x dx equals to integration of 0 dx. This would imply mx dx plus integration of, because px is y, ny dy equals to some constant c, where c is some constant. So c is arbitrary constant. So what is the upshot of this? So now if the antiderivative of, so if this integral, if antiderivative of what? If antiderivative of m and n are, say, g and h respectively, then what will we get? This would be, that means what is the meaning of that? Meaning is that g prime x equals to mx and h prime y equals to ny. Then using this, we see that we get gx plus hy equals to c. And then solving for differential equation means solving for y. So in which is a solution? This is a solution. And we solve for y if possible. Sometimes it may not be possible to solve for y because the solution is an implicit solution, right? Like equation of circle. Y is a function of x implicitly and locally. So sometimes it may not be even possible to solve and get an explicit solution for y. So this is how it works. This is why the solution works. Let's look at an example. Okay, so let's look at the following example. So dy by dx is x minus x cubed upon y plus 3. So it is separable. So it is separable, right? So this is separable because we can write it as x minus x cubed minus 1 plus y cubed dy by dx equals to 0, right? This could be your mx and this could be your ny, right? So according to our original description here, right? So mx plus ny dy by dx. So this is separable. However, to solve it, I will basically separate all the x and y on one side. So we get what? We get here, we get dy times 1 plus y cubed equals to x minus x cubed dx, and we integrate on both sides. Okay, this has to be written here. So now when you integrate on this side, you get y plus y to the power 4 over 4 equals to x squared by 2 minus x4 by 4 plus a constant c. Okay, right? Or you can basically multiply throughout by 4 to make it look slightly simpler. So this implies, or this implies what? 4y plus y to the power 4 equals to 2x squared minus x to the power 4 plus 4c. Or let's bring everything on one side. So x to the 4 plus y to the 4 uh, minus 2x squared minus, sorry, plus 4y equals to 4c. Let's call this another constant, c prime or c bar. Let's call this as c1, and then this will be called as c. All right, looks nice that way. So you get, this is a solution. Now this solution, as you can see, is an implicit solution, right? It's, you cannot solve for y from here, right? So implicit solution. So we cannot easily solve the equation above to get explicit expression for y in terms of x. So we leave it in the implicit form above. Given a particular value of y, one can use numerical method to find corresponding value of y. So in this case, we will use the numerical values. Now, let's try to see, consider the direction field of this guy. So consider the following solution we got. Now we'll see the direction field. The direction field can be seen. So you can download this GeoGebra file from the canvas and see the direction field. We'll see that here. So this is the direction field of the curve we are looking at. So as you can see, I have plotted this y4 plus x to the power 4 plus 4y minus 2x equals to c. And now I'm going to change the values of c. So let's see. So I'm changing the values of c starting from, say, from 0. So when first of all, c -5, there's no curve like that. But you'll see the curves are basically, as you start increasing the value of c from -5, you can see that in this case, what you get solutions. Now from here, you can observe some special properties of our solution. First of all, the integral curves, which are these solutions, they are symmetric in the what axis? They are symmetric in y-axis. Okay. Now, when C is large, so let's take large C. So if C is large, either you see either X has to be large or Y has to be large, right? So you see the equation looks more like X to the 4 plus Y to the 4 equals to C. So it's like a flattened circle, really, all right? Now, as C gets smaller and smaller, you can see there's an indentation on on Y axis. See, there's an indentation happening. You see, there's this indentation here happening on y-axis, right? Now, for small enough c, you will see that the curve splits into two parts. Yeah, so you can see for c equals to already minus 3, it starts splitting into two parts, and then later on it splits into two. So then the question is, how do you determine that critical value of c such that it splits into two parts, right? Yeah. So we can come about it to the next lecture. You should think about that part. So that's the idea. So you can download this GeoGebra file from the canvas and upload it on GeoGebra to see how it works. Okay. So this takes care of the discussion here. All right. So let's move ahead. So what is the summary of whatever we discussed today? So first of all, we write the how do we solve the separable differential equation? We first write the separable differential equation as mx plus ny dy by dx equals to 0. Right? Note that this need not be linear, right? N of y, for example, could be y squared or y cubed. Then you compute the antiderivatives of m of x, call that antiderivative of m of x as g of x, antiderivative of h of x as n of y. Then we get the general solution of form gx plus hy equals to c, where c is some constant. And then we try to solve that algebraically. Okay, so that's the idea. All right. Now, it was clear from the integral curves that in the previous example that the solution of the differential equation is only valid for some values of x. So only for some values of x, the curve is valid, right? So such interval of for x is called interval of validity of a solution. So let's try to find out what is the interval of validity for the following solution. So we have already found out what is the solution to this differential equation. Already found out what is the solution to this guy. The solution to this was y to the 4 plus x to the 4 minus 2x squared plus 4y equals to some constant c. Now, to solve this constant, to find this constant, we need some initial value, right? So in this case, we are given initial value as well. The initial y of 0 is 1. That means when x is 0, y is 1. So let's substitute that. When x is 0, y is 1, right? So we get when x is 0, y is 1. So you get 1 plus 4, which means c is 5. So we get what? So what is the solution to this IVP? So IVP has solution y to the 4 plus x to the 4 minus 2x squared plus 4y equals to 5. So now, if your y equals to phi of x is a solution to this differential equation, let me rewrite this differential equation from here. So what do I get? I get phi prime x equals to x minus x cubed over 1 plus, what is my y? Y is phi of x, so phi of x the whole cube. So look at this solution. So the solution phi of x is not differentiable, when what happens? When you get that denominator becomes 0, so 1 plus phi of x cube equals to 0. This means phi of x equals to minus 1. So therefore, all the x values that make y or phi of x minus 1 are not valid solutions, are not valid as a solutions. So they are not valid solutions. So what we'll do is we'll try to find out what are those values of x. So find what? So find values of x such that what? Such that what? Phi of x equals to minus 1 or y is minus 1, right? Or y is minus 1. They're the same thing. So let's work it out. So we get what? Y to the power 4. So what was the equation? The equation was y to the 4 plus x to the 4 minus 2x squared plus 4y equals to 5, right? And now I'm putting y equals to minus 1. So I get minus 1 to the power 4 plus x to the 4 minus 2x squared plus, sorry, 4 times minus 1 equals to 5. So this is going to be, bring everything on one side. So x to the 4 minus 2x squared minus, so minus 1 to the power 4 is 1, minus what? 1, sorry, it was 4 times minus 1. So I get what? I get minus, so 1, so let me write it down. 1 minus 4 minus 5 equals to 0. This gives me x to the 4 minus 2x squared minus 8 equals to 0. Now, this is a quadratic equation in x square, right? And what are the solutions? So you can see the factorization of this is x to the 4, sorry, x square minus 4 times x square plus 2 equals to 0. This would give me that x square equals to 4, or x square equals to, or x equals to plus or minus 2. This will not give me any solution, the second part, because square of negative x square, it can never be minus 2. So these are the things. So therefore, for these values, the solution will not be, there will be no solutions, all right? So now think about it. Your real number axis is divided now into parts, minus 2, 2. So now you have your solution is either here, or either here. But now recall y of 0 was our initial condition, right? So we're given, initial condition was given at x equals to 0. Therefore, the interval of validity is the one where 0 belongs. So 0 belongs to minus 2 to 2. Therefore, our interval of validity is minus 2 to 2. All right. So, yeah. So this is the idea behind it. So that's all for today, folks. Thank you.